I will send you the details on how to access the recording. So the question is, why is argon a bit bigger than chlorine, although we have said that across the period atoms get smaller? It is that, let us assume we are talking about sodium. Sodium is this big, 281, and it has 11 protons. Magnesium then puts one more electron into this shell, but has one more proton in the middle, so that the extra proton pulls it in a bit more. As we go across the period, the number of protons increasing is only increasing by one, but proportionally is less important. So if you go from 11 to 12, that's more than going from 15 to 16 as a proportion. As you go right to the end to argon, there are many. If you think about subshells, the third shell has 4 subshells, and by now they are all full. So they are all paired and they are repelling each other. And therefore, the increase in protons is not enough to pull them in closer. That's it. Okay, we're going to do some questions and answers now, I hope. But I have a couple of other things to tell you. Firstly, I had a question. I think it's from Ushirika, from a teacher at Ushirika, and I will show you it if I can find it. Yes. Let's go back. Let's go back one. Okay, here's the question. The question says one molecule of a hydrocarbon has a mass of 9.33 times 10 to the negative 23 grams. Avogadro's there. Find the molecular mass and what is it? What's its molecular formula? Well, one of the best ways of doing this is to, where's that gone? Is to think, okay, if the RMM, the molecular mass, is the mass of 1 mole of all of the molecules, then it's the mass of 6.02 times 10 to the 23 molecules. If each molecule weighs 9.33 times 10 to the negative 23 grams, then if we multiply those two together, we will get the mass of a mole of these molecules. So, what's happening? So the mass of 1 mole is its RMM or RFM. So 1 mole weighs the mole number times the mass of 1. So that's the mole number, Avogadro's, times the mass of 1, and that comes out at 56. Now it's a hydrocarbon, so it's CNH something. So if it was 1 carbon, that would be a mass of 12. Well, you can't have 44 hydrogens attached. So we just go, okay, 1 carbon 12, 2 carbons 24, 3 carbons 36, 4 carbons 48, 5 carbons 6. Okay, it can't have 5 carbons. So it has to have 4 carbons, and it weighs 56. Well, 4 carbons weighs 48, and therefore 56 minus 48 is 8, and it must be C4H8, which looks a lot like butene. Probably butene, maybe but1ene, maybe but2ene, maybe cis or trans or Z or E-but2ene, or maybe cyclobutane. Anyway, we don't know. Maybe 2-methyl propene. We don't know what it is, but that's the answer. I hope that's useful to the teacher from Ushirika. So if you get this question, or if your students get this question, you need to know that the RFM or the RMM is the mass of 1 mole of the particles. So there's the mole. So what does each one of them weigh? That's the top number. Multiplied together gives you the RMM. Okay. I hope that was useful. Now, I don't know if Kisumu is with us. I hope Kisumu is there. I can't see Kisumu. Hang on. Calling Kisumu. I haven't got Usharika. I don't know where they've gone. I hope these guys are going to come in just a minute. I will start anyway because they can watch the recording and we will just hope. Oh, this says there's something in the chat. No. Okay. Let me just see if I can get them to come. So I've got Kibera, Kisumu, Mathari, Kibera, Mathari, Wamwini. Let me just have a look. I'll see if I can see that. Hang on. Somebody is showing me something. I'll see if I can see the question. Explain why the reaction between chlorine gas and sodium hydroxide at room temperature is called disproportionation. Yes, I can do that. I will show you that. That's a question I will definitely be able to do. Okay, let's go back to this one. Here's the one from group 7. I just want to show you this one little bit of it. Here. At the bottom, look at this equation here. Oops, sorry. Here. H2O plus Cl2 goes to HCl and HOCl. If we look at the chlorine at the beginning, it is not bonded to anything other than chlorine. So although it has a valency of 1, it has an oxidation number, in other words, the charge on each one of the particles of 0. When it combines with the H here, the chlorine here will be now -1 because it's H. This is an acid. H is +1, chlorine is -1. Now in this here, because OH is -1, the chlorine must be +1. However unlikely that seems, it's +1. So the chlorine has gone from 0 to -1 and to +1. That is what we call disproportionation. So where something is oxidized and reduced in the same equation, that is disproportionation. The chlorine has gone from 0 to -1. In other words, it's gained an electron, that's reduction, and it's lost an electron in going to +1 here, that's oxidation. So 0 to -1 and to +1, disproportionation. Okay, I want to show you a couple of things before we take any other questions. I hope, hello, Teacher Wycliffe. I hope that that is making sense to people. But I want to show you something that I was going to end the last session with. In this, at the end, it says, leave the best till end, periodic table. This is the Royal Society of Chemistry in the UK. It's the oldest chemistry body in the world. And it has a particular periodic table, which I'm going to show you now. And I find it very useful in helping students understand things. It has a number of different features to it. For instance, here's a periodic table. And at the moment, it is showing which ones are solid, which ones are liquid, which ones are gas, and which ones we're not sure about because they're all relatively newly made or discovered, or nobody has looked at them. Up here at the top, there is a temperature scale which allows me to increase the temperature. So I can slide it up, and as I slide it up, I can see things become going from solid, the darker, going from solid, the lighter blue, to the darker blue. And you see very quickly, as I warm it up just a little, look, group 1 melts really low temperatures. Look, this is only just over the boiling point of water. So this shows that group 1 are really pretty soft and not very good bonding. Now, as we continue to heat it up, we will find other elements. So there's this great group here. That's not very interesting. But look what happens with group 2. Watch group 2. And group 2 is starting to become liquids, but already, although they've become liquids, group 1 have become gases. Now, that is proof that group 1 have much lower melting points and boiling points than group 2. Okay, so that's useful. Now we might want to go up and go, oh, look, what's the last element? What's the last element which is still which one is the last one to boil away? Oh, it's one of these 3. Okay, which one has the highest? In other words, these are liquids at the moment. Which one has the highest boiling point? And as I increase it, I'm using the plus here. As I increase it slowly, I'm left with W for wolfram or tungsten and rhenium. And as I increase it, I find that, wow, that's hot. That is seriously serious. 5,500 degrees Celsius. And they're still liquids. Ah, tungsten goes first. But as I cool them down and I drop them down to being solids again, you find they're solids later than other things. Yeah, almost everything else. And we're left with the same 2 as the last 2 solids. And as we heat these up, you would expect it to be rhenium, but rhenium boils before, melts before tungsten does. So tungsten has the highest melting point of any metal. Anyway, that's that. We can look at this table in a different way. So we can go, which ones are metals? And up here, we just click on metals. There are all the metals, which is proof to the students that there are many more many more metals than non-metals. Okay, there's the periodic table. Here are the non-metals, only a very few of them. Okay, very, very few. If I want to look at a particular element, I can. There's something up here which is quite odd. They had a competition, an art competition, international art competition, to come up with symbols for the elements which meant something about them. Now, some of them are fairly obvious. Say we take, excuse me, excuse me. This is baked beans. It might surprise you to know that there's actually quite a lot of nickel in baked beans, etc., etc. There's a lot of different. This is iridium, which is meant to be the dragonfly because it has iridescent wings and so on. So they're quite interesting. But nevertheless, get off that. The point about this is it can tell you about any particular element. So I can go and I can find out about, let's say, rubidium. And as I click on it, there is a huge amount of information about it, some of which is important, some of which may be quite confusing to your students, but it's got things like history and so on. But at the bottom, it's got videos. Now, I want to introduce you to a particular video, which is quite hilarious. A particular professor of chemistry who sadly is not a black young woman, but is an old white guy. But he is funny and he is quite well known on UK television for his chemistry. And if you want to watch videos, if you wanted to show your students anything about any one of the particular elements, you just pick the periodic table, pick the element, go down to the bottom, and there will be videos. When you go to the videos, some of them are private, that's run by the Royal Society of Chemistry, but some of them are not. So they're always a little introduction, and these videos...
Got a sample of sodium. Sodium is a very reactive metal. It's stored under an oil.
I'm going to just mute him. It shows experiments with a particular metal. It also includes this chap here, who will come in just a moment. This guy. This is the professor, not this guy. These are the demonstrators. This guy is the professor, and he talks about it. Now, he may be a bit off-putting to some people because he is so old and so funny, but the demonstrations are great. They do silly things. And if you want to show a really good demonstration of sodium reacting, then they do large-scale demonstrations, the sort of thing we can't do. And they obviously enjoy themselves doing it too, because there's quite a lot of laughter. Okay, so that's them. So it's quite a useful periodic table. I really think so. But the last thing I want to show you a presentation on before I take any questions, because I hope you've had a nice lunch and pretty soon you will start going to sleep. So I need to talk quickly now. So the thing I want to give you an idea of is this one. Now, some of you won't have any choice on what you teach. But if you do, and at some point you will, what I want you to do is to try and think about making the most of the course for student success. Now, I have mentioned not leaving the revision right to the end, doing little bits of revision on the way, but not much, and getting to the end of the course and then teaching people how to answer the questions. So this is my little take, and thanks to a teacher called Thaddeus for his notes on this, because I watched a program by him and I just stole some of his ideas. Not all of them. So it's about getting your students to succeed, and that's about forward planning. Firstly, you have to know your enemy. You have to know what it is that they will need to do at the end. Sure, we want them to have a great time. We want them to enjoy chemistry and learn about the world, but eventually we also want them to do well in the examination. This is the 2021 paper. It's an analysis. This is Form 1, Form 2, Form 3, Form 4 topics. This is the total number of marks on paper 1, on paper 2, on paper 3, and the total. And what is obvious first is that the Form 4 material is worth almost more marks than everything else put together. And so most of the marks come from Form 4 and Form 3. Hardly any from Form 1. But of course, if you didn't do Form 1, they wouldn't be able to do Form 2 and so on. But it means that we have to concentrate on the right stuff. It might be surprising that Form 1 got an entry in paper 3, but this was a cooling curve. And although you do it rather simply in Form 1, it was about drawing a cooling curve and then being able to recognize what it's about. About 30 marks on the whole paper anyway come from organic. About another 20 or so come from moles. So you need to pick on the big topics. So it's about knowing that Form 4 is the most important and therefore the one that you spend the most time looking at. And if you look at paper 1 and paper 2 is where the concentration on the difficult material happens. Paper 3 has bits of everything. Okay. Second, don't underestimate how much work there is to do. But like I said, this is not a good way to teach your students. If you just handed this out to students only one in about 30 or 40 would like to learn from this sort of thing. They want you to simplify this. Sure, you might find it useful to have this on your wall at the end when you're revising, but this is not a nice way of learning. Plan the attack on the enemy. This is about trying to predict how long we should spend on different topics. You will get this later in case you want to think about it yourselves. You may disagree. You may not think this is a good way of doing it, but I looked at the specification, the syllabus. I looked at Thaddeus's video, and I think this is sensible. So we talk about the topic and roughly how long it takes to cover it. So the introduction to chemistry, there is no point, as I said, in giving them spending 3 weeks finding 30 rules for the laboratory. It's a waste of time. Train them to be nice people, train them to be sensible, and you don't need that. Simple classification, introduction, this is all going to take term 1. Get them excited, make it interesting, show them videos, or if you can, show them the real chemicals. Don't worry that you are going to show them the same stuff later. Just get them excited. Get them to believe that they can do it. Form 1, Term 2, acid bases and indicators. That is the one where you might grind up some colored material and make an indicator. You might talk about why sour milk tastes sour, because it's acidic. Everything sour is acidic. You do a little bit about air and combustion, and then water and hydrogen. So that's the first 2 terms of Form 1. That's quite a lot of stuff. Now, I know of schools where that has taken the whole of Form 1. Don't. Cut it short. Remember, there aren't going to be, there are not going to be that many marks from Form 1. It's just foundation. Here's the next bit. Form 1, Term 3, structure of the atom and the periodic table. This is really important. They have to really get this. So you need to spend virtually a whole term looking at why the periodic table is as it is, how it works, finding out about the atom, about electrons, protons, neutrons, electron configuration, and so on. Then we move into the chemical families and the structure and bonding and all this stuff here, and the beginning of carbon is all in Form 2. Form 2, Term 1 is structure and bonding, basically, and a bit of the chemical families, which you've started in Term 3 of the Form 1. So Form 2, Term 2 is salts. It's only very simple at this point. It's the effect of electric current, which is very simple, and the beginning of carbon, carbon dioxide, and so on. It is quite important to realize that most of Form 2 work that is normally seen as Form 2 work will be completed by the end of Form 2, Term 2. In other words, the stuff which is normally given by KCSE as given as the whole of Year 2, Form 2, try to finish it towards the end or at the end or just into Term 3 of that, so you can start Form 3 stuff. Then we move into Term 3 of Form 2, and then we've got the non-metals. Put all the non-metals together because it's very simple stuff. There's an awful lot of chemistry which you're going to come across and you will have to revise, but it's important stuff. So give it a whole term and do all of the non-metals together. That is my suggestion. Then when we start Form 3, we do gas laws. People take too long on gas laws, in my experience. Those people who are not very arithmetically able will find this difficult because we have things like Boyle's and Charles and so on. But when you shorten it and you do not worry about the history, you've got to draw the graphs, but if you say to them, Boyle's law says P1 V1 equals P2 V2. I want you to find P2, here's P1, V1, and V2. They can do it. So give them a simple way of doing that, and then do them all. Now, we're in Form 3 here, but I'll tell you, for those of you who are thinking, nah, The mole is really, it's really, really hard. It's going to take them till Form 4 before they really understand it. I teach my equivalent of your Form 1, the mole. I teach all of them it in Form 1 equivalent. Okay? So, and they get it. They get it with no problem. They understand it. They can use it from Form 1. Okay? Then we get into the big lump of organic, and organic is huge, and it is, as it says here, a spotlight zone, because there are an awful lot of questions on organic, and there are many different questions they can. So this is Form 3, Term 2, virtually the whole thing, then a bit of metals. Then we go into the more complicated salts, acids, bases, solubility in Form 3, towards the end of Form 3. Energy changes, chemical and physical changes also in there. I think you have to realize that things like radioactivity, which we can spend a lot of time on, is also taught in physics. And a lot of students have an innate understanding of rate. We tend to give it too much time. So we can do it some other time. Then into Form 4, we do the rates properly, electrochemistry, radioactivity. Do not spend too long on radioactivity, as I have said. And then practice makes perfect. So in other words, you are trying to get Form 4, Term 1, Term 2 possibly. We are trying to finish the syllabus in time to practice. And the practice is all about going back, looking at things again, in the proportion that it shows in the examination. So most of it on Form 4, a bit less on Form 3, much less on Form 2, and almost nothing on Form 1. When you are revising, there will not be many questions which are going to be on Form 1. Show them tricks, show them easy ways of remembering things, but do lots and lots and lots of practice. The difficulty in this is that it sounds as though I am saying make the examination the focus of the whole chemistry course. That is not what I am saying. I am saying that chemistry is a brilliant subject. And if the students start to believe it's a brilliant subject, they will become good learners anyway. They will want to come to your lessons. They will want to understand. I've left this guy here right at the end, just because I owe him because of this, but also because I think he is an unusual teacher. I'm sure many of you are fantastic teachers. I really am. I am totally, totally sure that many of you are fantastic teachers. But I'm giving you an example of a person who works in a school which obviously gives him enough time to produce materials for other people. That's great. That's really kind and really nice. And it is sometimes a shortcut for you to look at somebody else teaching a particular topic. Okay, that's basically me. So we have 25 minutes or something like that. Do people have questions about how to do something, how to approach a particular subject or anything like that? Because I would like to hear from people who are interested and do not know how to approach something. Now, I may not be able to answer it because, just like you, I am not, my syllabus is completely different from your syllabus. Okay, completely. So I teach one syllabus and you might well ask me a question about something horrible and I don't know the answer, but I can tell you where to find it. There is nothing wrong with not knowing the answer. So, questions. Anybody got a question? Otherwise, I will make some up. Hello, Kusumu. You have a question? Oh, we have a question there. Hang on. Let me just pin you. Let me just see. What does isoelectronic mean? Okay. What does isoelectronic mean? Isoelectronic means they have the same number of electrons. So let us say that we have sodium and magnesium atoms. Sodium atom has 11 electrons. Magnesium atom has 12 electrons. but their ions, sodium losing 1 down to 10, magnesium losing 2 down to 10, they are now isoelectronic. When they ask the question, they normally ask about something, one thing which has lost electrons and another which has gained electrons. You just have to look at them. Isoelectronic, the same number of electrons. Okay, next question. Be courageous while I drink some water. I hope lunch was good. Was lunch good? You better have gone to sleep. Oh dear. A question. Hang on. Let me just have a look. Where are we? Hang on. What name is given to forces between solids? Is that solid liquids and gas particles? Okay, that's yes, okay. The forces of attraction in solids, liquids, and gases. The usual term is van der Waals. That's VAN, like van. I'll come to questions in just a minute, gentlemen. If you, I'll tell you in just a minute, Teacher Wycliffe as well. Van der Waals, but there are van der Waals is a term that means all forces of attraction. Electrostatic are between ions, charged particles. So between Na plus Cl minus, etc. But in KCSE, I have noticed they use the word van der Waals for those attractions which are the weakest attractions. That is, those between things like noble gases, between gases which are not attracted to each other. Have you heard the term hydrogen bonds? Yes? Everybody should have heard hydrogen bonds. Good. Thank you for the thumb. That's very good. So hydrogen bonds are the bonds that form between molecules containing hydrogen attached to nitrogen, oxygen, or fluorine directly. So water, HOH, ammonia, NH3, hydrogen fluoride, HF, ethanol, C2H5OH, anything with hydrogen attached to N, O, or F. My students remember not often found. Hydrogen bonds are not often found, except on this planet, where they are very, very important. So van der Waals for the weakest forces and hydrogen. Teacher Wycliffe area, you had a question. Oh, hang on, I have a question here from somewhere near Mike. I'm just going to take it from Wycliffe's one. Let me pin so I can see it properly. Can a student pass chemistry by reading Form 1 and 2 notes only? Yes, they can, actually. Yes, they can. The trouble... Yeah, it's a good question. It's a very good question. The question is, could we get people through the examination if we only taught Form 1 and Form 2? And the answer, the simple answer is yes. They can get enough marks, but it varies. Each year there is a variation in the number of marks for each form. And some years the number of marks for Form 1 and Form 2 are quite small. And the other problem is that if we teach them only Form 1 and Form 2, they have to get 100% on Form 1 and Form 2. And I think it is easier to teach them Form 1, 2, and at least 3, and some parts of 4, and then they will be able to do better. We have another question. Is that the Kasumu team? Hang on, I think we had one from, do we have one from Kasumu? Let me, hang on, I just have to pin you so I can see the bigger, I have to make it bigger, I have to make it bigger. Identify the group which an element K. So identify that, sorry, let me just pin that so everybody can see it. Let me just hold on to that just a minute. Let me see if I can. Oh, it's not sharing. Hang on. Okay, that's a very strange question. I'm not. Did the question say that K is an unknown element? Kisumu. Kisumu, look at your. Come and talk to me. Come and talk to me. Turn on your microphone. Turn on your microphone, please, teacher. Okay. So we had a diagram which was circles with positive charges in, and then it looks like double negatives for the same thing. Was the question, was it saying that K was an unknown element?
Yeah, K is the structure bar. This is the structure of element K.
Okay.
Yeah.
That's the structure of one atom? No, that must be of a piece of K. If it has lost 2 electrons, it must be in group 2. But I don't, can you find the question printed somewhere? Because there's something funny about that. I'm not doubting you. I'm trying to see it better. Let me just see if I can make it right. Everybody can see it. Hold it up a bit. Okay, look at this, everybody. Okay, here's element K. Okay. And it's showing all these positives and then 2 negatives. Now, this is suggesting this is metallic bonding with 1 plus charge on the centers, and it's picked up an extra electron. Now, that is unusual. I don't entirely understand that question. I'm sorry. Sumo teacher, do you know where that question came from?
Yes.
Do you know do you have its original source?
Yes.
Could you find it, please? We're going to take one from Michael. Hang on. Oops, it's gone off. Your phone has gone off. Can you get your phone back on? Oh, come on. Okay, let's see if we can see that. Oops, not that one. Here we are. Okay. Okay, everybody, I hope you can see this. Everybody's going to work on this together. So T, 2.34 grams, T displaces 3.20 grams of copper from copper sulfate. Charge on an ion of metal T. Okay, all right. Everybody have a look at that. Just hang on to that, guys. Just hang on. Okay, let's see what's happening. So we've got T has an RAM of 69 and copper is 64, which we know. Okay, let me see if I can write this on a piece of paper. Hang on, let me just take a picture of yours. Hang on, just a moment. Okay, so let's see. Okay, I've got that. Thank you. Thank you. So I'm going to see if I can find a screen that I can write on. Let's see if I can write on this one. Let's add a... Let's see if we can write on this. Okay. So we have, if we can write, oops, not that. Sorry. Okay. Here we go. So we have, I hope you're seeing, CuSO4 plus T turned into TSO4. We don't know whether it's 1-to-1, and copper. Okay, we started with it produces 3.20 grams of copper, and we use 2.34 grams of T. Whoops, sorry, it's going funny. Oh no, don't do that.
Kisumu team, kindly mute.
Okay. So here we are. So that's grams there. Okay. Now we know that the AR, the RAM of T. Can we just mute, please, guys? Can everybody? I don't know which team it is. I can't look at the same time as I'm doing this. Okay. So the moles of copper. If we assume that the moles of copper is 3.2 divided by the RAM of copper, then that will be 3.2 divided by 64 that must be a 20th, 0.25. Sorry, 0.05. Now, if we do the same for T has one, I think they said, of 69. So 2.34 we have to divide by 69, and that comes out as 0.034. They are very strange numbers. So so if we take that, then we need a ratio of those two. So if I take 0.05 and I divide it by the smallest, 0.034, I find it's 1.5. So the ratio of these is 1 to 1.5. That is 2 to 3. In other words, that is the ratio in here. Okay, so that is 2 of this. This is of this. We have to go 3 here and 2 here. And that means 3 T's are taking the place of 2. So this would have to be 2. This would be 3. And therefore, it's not TSO4 like that, not like copper sulfate, because if 2 coppers have plus 4 pluses, then the 3 T's must have the same. Well, 3 times 4, well, 3 over that is saying it's 1 1/3. So there is an error in the question. What it is suggesting is that the T is has a charge of 1 1/3, which is not possible. So what they are saying is that there are, sorry, let me just use the rubber. Let me just use the rubber. Hang on. I'll show you what
Cerebrum. Cerebrum.
So this is going to be, sorry, let me just get my pen back.
Cerebrum.
So this is 3 SO4. So we've got the SO4, which would make it aluminium sulfate.
Describe how intercostal muscles influence inhalation in mammals. So, unaona hiyo process ya breathing, mechanism of breathing.
Hang on just a minute.
Internal intercostal muscles. External intercostal muscles.
Mute everyone,
Just a moment. So,
can mute everyone.
So, ladies and gentlemen, firstly, I can talk about intercostal muscles, but intercostal muscles are mainly biology, and teacher Matt is not here today. It's true the intercostal muscles have to expand and contract, and the diaphragm has the need to go up and down for you to breathe. But I'm not going to do breathing today. So in that question there, we had to find out the moles of T and the moles of copper and relate them. And it's 3 to 2. So 3 coppers plus 6, 2, it is likely to be aluminium. Okay, it's likely to be aluminium. It's not aluminium because it doesn't have an RAM of 69. If I were you, I would have looked on a periodic table for an element with a RAM of 69. Another question, please. Okay, let's have a look. Other way up, please. Upside down, please. That's it. Why is it that silicon... Hold it a little bit further away, please. Thank you. Why is it that silicon oxide has a giant structure while silicon chloride has... Yeah, okay, good question. Good question. Okay. This is because... Thank you very much. That's very good. A good question. Why is SiO2 a giant molecule, but SiCl4 is simple molecules? It is because the oxygen has a valency of 2. And the silicon to oxide to oxygen bond is very strong. And when silicon burns in oxygen, and it does, when silicon burns in oxygen, then it forms silicon to oxygen bonds, and it tends to form bridging bonds, SiO, 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 and so on. With chlorine, with only a valency of 1, when the silicon has bonded to one chlorine, the chlorine can't bond to another silicon. So the silicon, I'll see if I can show you that on a drawing. Let me just see if I can show you it on a drawing. Oh, come on. No, not that one. Sorry, I'm just trying to find somewhere where I can show you it on a drawing. Okay. Get rid of all of this. Okay, so silicon tetrachloride, silicon and chlorine forms a molecule which looks like this. So I'll try to draw it. Okay, silicon, tetrachloride, Si in the middle, chlorine above, chlorine here, chlorine here, chlorine here. Okay, the chlorine has a valency of 1, so it cannot form a bond to another silicon. But silicon can attach to another silicon via an oxygen, and so it does this. So the reason it forms a giant molecular structure is because it does this. And because it can do this, because the oxygen can form a bridging bond, this is what happens there, like that, on and on and on, that makes it a giant molecule. So the silicon chloride cannot form a giant molecule. It has to be simple molecular. So anything that has more than a valency of 1 could do this. So we could have, for instance, we could have sulfur between silicons. But that's it. Okay, I hope that helps. I've got something in the chat. The chat says... Oh. Nothing. Okay. Get rid of that. So another question. Your questions are very good, guys. They are very good. They are sensible questions. So let me just... That's upside down. Turn it upside down, please. Here it is. Here's another question. Let's see if we can do this one. Oh. The other way up, please. That's it. That's it. And hold it very still. Oh, your bandwidth is very low. Hold it very still. I can't read it. Oh, hang on. Hold it a bit flatter to the screen. I'm nearly there. Okay. Why is hydrogen placed in group 1? Yes, I can see that. What's your second question? Up a little bit, please. Up. And hold still. I can't read that one. Can anybody else read that one? Anyway, it doesn't matter. I'll tell you about the first one. You can just unmute. Just unmute and tell me. But the first question was, why is hydrogen shown in group 1? Hydrogen is sometimes shown in group 1, sometimes in group 1 and group 7, and sometimes in the middle of the periodic table. It is shown in group 1 because it has 1 electron in the outermost shell, but that doesn't make it a metal. It can't form metallic bonding. It is sometimes shown in group 7 because its shell only holds 2 electrons, so it needs to pick up only 1 electron, just like group 7. But most of the time it is shown on its own in the middle. I think we have another question here. Let's see if we can spotlight for everybody. Okay, they're very good. I hope everybody can see that. Hang on, let me just remove one pin. Right, here's the question, guys. Everybody look at this, because it's nearly the end of the time, but I want everybody to understand this because it's a very good set of questions. Are chemistry simulations important? How can you access them? And what teaching and learning materials can one use in the teaching of organic chemistry? Okay. To my mind, simulations are important. Let me just... So, I just need to remove the pin from you guys. Sorry. Okay. All right. Why is Michael still showing? Michael, remove. There we go. Okay. Hopefully you're going to come back to me. No, for some reason, Michael is still in charge. Anyway, simulations are important. There we are. Simulations are important. There are 2 different kinds of simulations. Simulations meaning showing a video, I think, is the question. I believe that it is possible to do chemistry without ever seeing the chemicals. But if you are going to excite your students, then I really think they need to see things. Now, it may be that you do not have a projector, that you do not have the ability to show videos to everybody. But I have been reading about the possibility of trying to get projectors into schools. I've been reading about trying to get solar panels on roofs so that there is electricity even when you have a power cut. At the very worst, what I have done with my own students when I haven't had a computer available, or if we are working out, sometimes we go out and we sample a river to see if there are toxins in the river. I ask them to take their phones. Many students have phones. And if you can get to an area where you have Wi-Fi, even whether it's in a cafe or whatever, it doesn't matter. They can see them, and you could set them to watch a particular video, just a little short one. If you can find it and embed it as a hyperlink, they can watch it. Oh no, what was the second question? Oh yes, what do you use teaching organic? I am lucky that I have these. molecular models, and maybe we should try to provide molecular models for the laboratories, because then you can make them. It is good, but it is also important that the students learn to just draw molecules, many organic molecules. They're not difficult. You can draw them. You can make them draw three-dimensional pictures, and that will be it. Now, I'm really sorry, but we have run out of time. I will be here in case anybody has a private question they want to ask. I hope it has been useful to you for some of the time. I will send the presentations, not just these ones, but also the ones on organic chemistry and electrochemistry, and I will send them to Michael now, and so you should be able to access them quite easily. I will also stop recording now,